In this video, I'm going to show you how you can extract data from a NetCDF file using R and write the data to either a CSV file or an Excel file. I'll start by showing you how you can do this for variables with one dimension, which could be, for example, a time series, or in this case, a vertical profile. And I'll then show you how you can do this for variables with 2 dimensions and with 3 dimensions. You can find all the code that we're going to use in this tutorial, along with explanations, by following the link in the description of the video. But without further ado, let's jump right in. There's 2 libraries that we're going to use today within this tutorial. The first one is called R NetCDF, which helps us work with NetCDF files. And we're also going to use a library called Write Excel, which will help us export the data to an Excel file. So let's go ahead and load those in. If you haven't got them installed already, remember to do so by doing something like install.packages and in quotation marks the name of the package, like this. I've already installed in my system, so I won't bother doing this today. So now let's have a look at the first dataset we're going to work with today. These are some CTD data from the Nansen Legacy project. We have a single CTD profile in one NetCDF file, been collected here, just to the southeast of Svalbard. If you use these data, make sure you cite them appropriately using this recommended citation here. Now, these data are available over OpenDAP, and you can see this link here. And basically, OpenDAP allows you to access data over the internet without you having to download the data to your computer first. You can just copy this OpenDAP URL, and if we return to our studio, we can give the URL as some argument here. I'll copy this URL into the description of this video, so you can just go and copy and paste it from there. Then if we want to open these data from the NetCDF file using our NetCDF, all we have to do is do data is equal to open.nc and this URL. And I'll print these data below just so we can have a look at them as well. Print.nc and data. And if I run these 3 lines of code, we see that the NetCDF file contents have been printed in this console. So I'm not going to go through this in too much detail. I have a separate video earlier in this playlist that shows you how to open and understand the contents of a NetCDF file. So just briefly, I'll show you what we want to do here. We scroll right to the top. It's quite a large file. We see that this file has a single dimension, pressure, and that every variable that has this dimension must have 320 points. So let's have a look at how we can load in these data from the pressure variable here, and perhaps also the temperature values and the salinity values. So I'll close this console again. So firstly, to extract these pressure values, we're going to extract them to a variable called press. And there's a command var.get.nc, var for variable. Open our brackets. Data is our NetCDF object here. And the name of the variable that we want to load. You can see this in the description here. So in this case, it's called press, which you can see here in the console. So if I run that, and then in the right-hand panel, you can see these pressure values have been loaded. Let's go through our other variables as well. So maybe temp for temperature, same syntax, var.get.nc, from the same data object. And this time, the variable is called temp. I'll run that. And then for the salinity, we'll call it psal. And write var.get.nc again. Data. And the variable is called psal. Now we run that. And now what we want to do is combine these 3 variables into a single data frame that we can export. So a data frame is basically a table of data. And this is commonly named DF, and we can write data.frame to initialize our data frame. We're going to include a column called pressure, which is going to have the values press, then a comma, a second column called temperature, which is equal to temp, and finally salinity, which is equal to pcell. If I run this, we can click on this data frame here, and we can see this has been created. Now to export these data, let's do it first to a CSV file. We can do write.csv. The thing we want to export is this data frame, so df. And then we want to give it some file path. So I'm just going to go home, look cdd data.csv. And if we don't want these row names, this index column here, to be included in the CSV file, you can just do row.names and make that equal to false. If I run that, and I'll go and find that data to show you, and there we are. You can of course load these into Excel just like this, but if you want to write them directly to an Excel file, an XLSX file, you can do that by just doing write_SLXX. And the syntax is very similar to above, so it's df for the object you want to export, some file path, and if you run that, and let's have a look at those. And I'm a Linux user instead of a Microsoft user, so this is LibreOffice. But you can see the data here and it should look pretty much the same in Excel. Okay, so now moving on to extracting data from variables with 2 dimensions. We're going to use the same 2 libraries. This time we're going to use some sea ice concentration data. And you can see the recommended citation for them here. I'll put a link to the dataset below. And I'll also put a link to the OpenDAP URL in the description. So the URL is like this. I will paste this in. We can do data open.nc and open the data from this URL. And let's print the data, print.nc data. And then if we run all of those, and we open up the console to have a look at the data, and scroll up to the top. So in this file you have 4 dimensions. You have XC and YC, which define the grid. You have a time dimension, which is unlimited, but currently there's only 1 value. And you have this NV, which is usually number of vertices. And this isn't so important for what I'll discuss today, but basically this is for if you have data that are representative of cells instead of discrete points. If we scroll down a little bit, the variable that we're going to try and load in today is this ice concentration variable. You see this actually has 3 dimensions, XC, YC, and time. But as I mentioned, time is 1. And so this is essentially just a 2-dimensional array of data. So first we're going to load in the data from this XC variable, which is a 1-dimensional variable with just the XC as the dimension. We'll load in the YC variable as well, with just the YC as a dimension, and the ice concentration data. And once we've got those and we've dumped all the data to a data frame, we'll also load in the latitude and the longitude variables. And in this case, we have 1 latitude value for each X and Y pair. So the latitude and the longitude are also 2-dimensional variables. Okay, so now let's minimize this console. We'll try and remember the names of the variables we're going to load in. And let's go and load those data in. So we can do XC and load in var.get.nc, similarly to before. Data, and xc was the name of that variable. We'll load that, and then do the same for yc, var.get.nc, the data object, and the name of the variable again. Then the ice concentration. This is, of course, a two-dimensional array, but the syntax for loading the data in is exactly the same. It's again var.get.nc, the data object, and the variable is called ice const. And now I've loaded that in. If you want to show that this is actually two-dimensional and not three-dimensional, you can do dim in the console ice conc. This will tell you the shape of the variable that you have, and you can see it's 864 by 864, so just 2 dimensions. So now, how do we combine these data that are in one-dimensional arrays for the xc and yc with these data that is in a two-dimensional array? Well, if we're creating a data frame, we need to flatten out these ice concentration values. So instead of having a 2D array, we have a one-dimensional list of values. But we've got to make sure that the values in that list are in the correct order. So let's have a look back into the console at that variable. And the order of the dimensions is what we're looking at here. We have xc first, and then yc. And what that means is that the values are sorted so that all of the CI's concentration values for a single xc coordinate come first for the whole range of yc values. I hope that makes sense. So to convert this two-dimensional array into a one-dimensional vector, I guess you could call it ice conc vector. Make that equal to as dot vector and the ice conc variable. If I run this, and now if we look at this variable on the right hand side, we can see that this is just a one-dimensional array now. But of course, this array has 746,000 values, whereas if we go down, the xc variable has only 864 values. So what we need to do is extend this xc coordinate by repeating the first value in this array, this minus 5,394, 864 times. Why 864, you might ask? Well, that's because that's the length of this yc dimension. Before we then move on to the second value in the xc, minus 5,381, and repeat this 864 times. So, unfortunately, there's a command to allow us to do that. We can do xc repeat, and the command is rep. We're going to repeat the xc, and we're going to repeat each value to the length of this yc, this 864. So if I run this, we see now that the number of elements is 746,000 in a 1D array. We need to do something similar but different for the yc values. This time we want to first have all of the 864 yc values at the beginning of the array, and then we want to repeat that array 864 times. So we can do yc repeat. We're going to use this function rep again. This time we're repeating the yc, and instead of using each like we used here, we're going to use times to repeat it a certain number of times, and that number of times is going to be equal to the length of xc. So we run that. So now we have our three lists of values, which are all 1D and all the same length. So we can then create a data frame the same way that we did for our one-dimensional data. We can do df data.frame. We'll start a new line this time. Let's create a column called xc. which is going to be equal to these XC repeat values. We're going to have a YC column, which is going to be equal to YC repeat, and C ice concentration, which is going to be equal to ice conc vector. Let's run that. And if I have a look at this data frame, there we are. The values are 0 a lot at the start, but that's because you wouldn't expect to see sea ice at lower latitudes. So now let's add the latitude and longitude variables. We can get them first with latitude is var.get.nc, data and lat. That's the name of the variable. And we'll remember this is a two-dimensional array of values with xc and yc as the dimensions. So we need to do latitude vector is equal to as.vector latitude. If I run both of those lines. If we want to add those as a new column in our data frame, we can just do df and the $, the name of the column that we want, let's call it latitude, make that equal to the latitude vector. We're going to do the same for longitude. So longitude var.get.nc from a data object and lon longitude vector as dot vector longitude, and add them to the data frame df $longitude vector. Let's run those lines again. And now we'll revisit the data frame, and there we go. Writing these data out to a CSV file is then just the same as what we've done previously. We can do write.csv df for the data frame, some file path. So let's go home, Luke M, C, ice conc dot CSV. And to not include the index column, row.names equals false. That all has to be capitals. Or we can write the data to an Excel file, write underscore XLSX. I'm going to copy and paste this because the syntax is the same. Just make sure I change the extension to SLSX. And run that. This might take a little bit of time to run. This is a lot of data, and it will also take quite a long time to open into Excel too. Once you have it going, it should look something like this. And just to show you that there are values there, if we scroll down to some data with a higher latitude, you see we start to get some values that are not 0. Okay, so now we're going to move on to downloading data from a 3-dimensional variable. We're going to use some data that we used in the first tutorial in this playlist. And this is the NOAA Global Surface Temperature Anomaly dataset. If you use these data, you should cite them as stated here. I've put all of these citations in the description for the video. To access the data, you can go to here, access via threads. This.nc will take you to the OpenDAP link. You click on this. This is the OpenDAP data access form, and you just need this data URL. So we'll copy that, and we'll move on to a new script for 3D data. Again, let's give the URL. It's equal to this. I'm going to remember to clear my environment this time. So this URL here, let's load the data in as we have done twice before. Data is open.nc and load it from this URL. And again, let's print them, print.nc data. Opening the console to have a look at the data. I scroll up to the top of this file. You can see there's actually 4 dimensions in this file: latitude, longitude, time, and Z, which is some vertical dimension. But because Z is equal to 1, which means there's only data from one elevation, these data are essentially only 3-dimensional. So we have this anomaly variable that we're interested in, which says it has 4 dimensions, but because Z is equal to 1, it's just 3 dimensions. I repeat myself, but off we go. So let's load the data in from the 1-dimensional variables first. We have lat is equal to var.get.nc data and lat. We have lon, which is equal to var.get.nc from the data object, and the variable is called lon. And time, var.get.nc from a data object and time. Now, if we have a look at these time values, we can see that the data are actually numerical values, integers. Well, if you haven't seen the first video in this tutorial series, I'll show you again here. If we scroll up, we can see time has units days since 1800. So each value is the number of days since this date. And the format is float, which is numbers potentially with decimal points. So we would expect these to be numerical values. Now, many softwares like Xarray in Python or Panoply can understand these units and will actually convert the time into readable timestamps as you load in the data. Unfortunately, our NetCDF doesn't do that for you, so we're going to have to convert these times into timestamps ourselves. So the start date is equal to as.date, and the first date was 1800, 0101. And then we can make an array of timestamps we're going to call timestamps. They're also going to be date format, and we're going to use this time variable. And we're going to say that we want these data offset from some origin time, which is start date. So now if we look at this timestamps variable, we see that the first value is the first day in 1880. And the second value is the 1st of February in 1880. So we have one value per month. Now let's get our anomaly values. We can do anom is var.get.nc data, and the variable was called anom as well. I will remember that this is a 3-dimensional array of data, but we want to flatten this out into a vector, so we can go anom vector is as.vector anom. And if we look in our console, the dimensions or the shape of anom, we can see it here. So we have 72 points of longitude, that comes first, 36 points of latitude, that's second, and 1,716 times. So let's first extend this first dimension, this longitude value. So when we extend this dimension, we need to first repeat the first longitude value 36 times 1,716 times before we move on to the second longitude value. So the logic is similar to what we did for a 2-dimensional variable, but we can do it here. Lon repeat. And we're going to use this rep function again to expand our lon variable. And we're going to repeat each value equal to the length of our time multiplied by the length of our latitudes. So repeat each longitude value 36 times 1,716 times. Okay. For the latitude, we can go lat repeat. Again, using this rep function. And this requires a bit of thought. So we need to repeat the first value of our latitude 1,716 times, which is the number of times we have. Then once we've reached our final latitude value, so after each latitude value has been printed 1,716 times, we need to start again with the first latitude value and repeat all of that 72 times. I do feel for people who have to do this in R instead of using Python, I am aware of a few different libraries that are being developed which will do this automatically for you, but for the meantime, think that over and hopefully you can get the logic in your head. So we're going to embed within this a second repeat function to repeat the latitude value, each value the length of our time, and we're going to do all of that a certain number of times, and that number of times is equal to the length of our longitude. So repeat all of that 72 times because we have 72 longitudes. Okay, we'll run that. And finally, with the timestamps, we have timestamps repeat. And this time what we're going to do is again use this rep function. We're going to repeat our timestamps value. We have 1,716 timestamps. And this is the final dimension. So we're going to go through the whole list of timestamps first, and then we're going to repeat all of them a certain number of times. So we can do times, and that number of times is equal to the number of latitudes times the number of longitudes. So it's equal to length lon times length plat. Then to create our data frame, we can just do df is data.frame again, and we can write all of our data to this data frame. So we're creating separate columns for timestamp, latitude, longitude, and temperature anomalies, and making those equal to our one-dimensional variables. This data frame has over 4 million rows now. I certainly wouldn't recommend exporting all of that to Excel. I don't think you're able to load that number of rows into Excel. But we can export them into CSV. So write.csv df, and where we're going to write that is home Luke M for me, and 3D data.csv. And we're going to do row.names equals false because I don't want the index column. If you do want to write this data to Excel, perhaps the data file that you're working with has less values, you can just do write underscore XLSX, and the syntax is the same. Just make sure you change the extension to XLSX. If you found this useful, like the video and subscribe so you don't miss the next one. Thanks very much for watching, and see you next time.